So previously we talked about different models for atomic theory, and this at first may not seem like one, but this is currently the model of what all atoms and molecules look like. And it's going to be a little bit fun to figure out at times because if we really want to understand what an atom or a molecule is doing, right there, that's the equation that we'll have to solve. And obviously, there's a lot going on here. So we're going to have to take a little bit of time, figure out what this means, how we use it, how we're going to see it in class, and how we need to understand it. Basically today, what we are discussing is the Schrödinger equation, which will be used for all of our understandings for basically all atoms and molecules forever and ever. So we're going to start off on a little bit easier version of the Schrödinger equation. So the Schrödinger equation here can just be manifested as H psi equals E psi. And that was developed by our friend here, Erwin Schrödinger. And this is all built off of understandings of wave theory, wave mechanics. We talked a little bit about waves and thinking about particles, and Schrödinger said, hey, when we're thinking about small particles like electrons, we should apply wave properties to them. And this equation will allow us to do it. Now, obviously, it's a very simple looking equation, and it is deceptively so. So it's complicated. There's a lot of bits to this. So we're going to go through these things and try to figure out what each one of these are so that we can understand them a little bit better. We will not, however, go into the deep, dark areas of the Schrödinger equation. Really, where you learn about this is in PChem, so we'll leave that for another course. Here's just an idea of getting it into our heads and saying, well, okay, this is what's here. How do we use it for what we need? We're going to not worry about some of the deep meanings and all the mathematics behind it. That's another course, but we'll need to use it for this course. Now, first bit that we're going to have to think about is this psi factor here, and what does it do? It's a mathematical function, so it's an equation, and what it does is it's going to describe all the 3D properties of the electrons that are around our atom or later on around our molecule. That's what it does. It describes all of the three-dimensional properties, okay? E is a little bit more simplistic. It's just the energy of the electron that's described by that psi. So it's just an energy. What does that energy look like? What does it mean? We'll talk more about that here in a bit. But for right now, just know it's just a basic energy. That's all we're getting here. So really, when we solve this equation, what are we always after? What we want is that energy. That energy contains all the information that we're really going to need, but to get there takes a little bit more doing. If we want to look at H here, H, you might have noticed, actually has this little hat on top of it. That's something very specific. It tells us that it's not a variable that we're dealing with here. It is an operator. Probably very few of you have heard of this term before, but an operator, really simplistically, it's just a set of mathematical instructions. For example, if I wanted to multiply something by x, that is an operation, to multiply by x. So in other words, that operator would be given the form x hat. If I wanted to, for example, multiply by y, I could have the y hat operator. Maybe my operator, I'm going to give it a generic label of a, and a just says we're going to take the second derivative with respect to x. So these operators, we're going to see them all throughout here, but they're just going to tell us about what math we actually need to do here. H is a very specific operator, which is used for a purpose. If we use H, this Hamiltonian operator, it's used to calculate the total energy of the system. Reminder, that means kinetic energy plus potential energy for our systems. And the set of mathematical instructions that we have is kind of complicated. Oh, great, I've got an alarm going off in the background. Hold on. So this set of mathematical instructions It's complicated, and this is why we'll teach this to you in another course. But here we've got some basic things where we're going to multiply by some stuff, and hey, these are all just constants up in here, so nothing too terrible over here. But then we have this part over here where we're going to look at the second derivative in terms of x, y, and z. You might be able to figure it out. That's because we're dealing with three-dimensional systems, so we have to take the second derivative with respect to each coordinate that we have. And then we're going to subtract off some pieces here that are all, again, constants, but multiplied by something that, again, deals with the 3D nature of the system here. And really, this is where we can start seeing, hey, there is a kinetic energy part, which I could underline here in green. Whereas the second part over here is going to be telling us about the potential energy of our system. So there's a lot of stuff that's encoded here. Again, we're not going to really focus on the math and how to solve this, but I'd like you to at least know what's behind the scenes here. Lots of math, but math that you've done before. You can do second derivatives. This isn't necessarily easy, but you could totally do it using Calc 1, Calc 2 knowledge that you've had. All right, so that's our brief introduction to the Schrödinger equation, just seeing what it is. Obviously, we did not spend a lot of time talking about psi here, and psi is going to be an important one. So we're going to come back in another video to talk about that, so we'll see that a little bit later. All right, that'll do it for this video. As always, you got questions, you got concerns, let's talk about them. Make sure to ask questions in class, throw me emails, whatever you need to do here, and we'll get you taken care of. But until I see you next time, be excellent to each other.